introduce our next speaker, Professor Kate Larson. Professor Larson is a professor in School of Computer Science at the University of Waterloo. She also holds a university research chair and Super AI fellowship. She is broadly interested in issues where a group of agents interact with each other. These agents may be AI agents or maybe human beings, and also maybe a combination. She is particularly interested in game theory, group decision-making, preference, and value modeling, and the insights that reinforcement learning can bring into these problems, along with the ways of promoting cooperative AI. Today, she will share her experience and expert opinion on cooperative AI. So it's an interesting topic. Please join me in welcoming Professor Kate Larson. Over to you. Thank you.
Okay, thank you so much. And thank you so much for the invitation. I've really enjoyed my visit so far and looking forward to spending the rest of the week here. So let's see if I can just share my screen. Okay, I think we're good to go. Right, so I'm Kate Larson. I'm from the University of Waterloo in Waterloo, Canada. As I said, I'm delighted to be here. It's an opportunity to meet sort of a long-term colleague, Dr. Fatima, and I'm also looking forward to meeting Professor Jennings a little bit later, who I've known for a very long time. What I'm going to talk about today is sort of a research agenda. So I'll be talking about sort of a vision that I've been thinking about with colleagues, and we've written sort of a recent kind of opinion piece. And then I will be giving examples from my own research to sort of illustrate kind of, I think, some of the interesting research opportunities. But I just want you to remember that I'm trying to sort of argue that this is sort of a really interesting space for AI researchers, and we need to be thinking about it quite seriously. So first, going to start with a quick introduction as to well, who I am and what I find exciting research-wise. So I consider myself to be an AI and a multi-agent system researcher. So I'm very interested in interaction. So I'm interested in environments where we have these multiple interacting agents. And whenever I use the term agent, I really mean decision maker. So my work, these could be software agents. They could be sort of theoretical constructs. I also collaborate quite closely with colleagues who do human-computer interaction, so I care about humans. I've never worked with robots, but that could be really cool. But I'm interested, as I said, in groups, right? So, and decision-making. So I care about things like, if I have a bunch of agents or decision makers, like in this room right now, how do we make a decision which on behalf of a group, which appropriately reflects kind of what we care about. So what our preferences and values of the group members are. And what does a good decision mean? I'm very interested in sort of use of game theoretic models in computational settings. So I spend a lot of time thinking about strategic behavior that might arise through interactions, particularly in situations where there are constraints that might come from computational limitations, information that we have about preferences or how we can express preferences, as well as information limitations. And then finally, I look at problems kind of related. So like, how do we reason about and design sort of systems or institutions that can sort of support our decision makers, in particular support kind of good group behavior, where I'm interested in understanding what good means in a variety of different contexts. So at heart, I will confess that I am a theoretician. My original degree was in pure math. So I love the theory, I love axiomatic methods, I like proving things. So some of my work is very much looking at theoretical foundations of multi-agent systems, particularly in strategic settings, where there is some amount of uncertainty kind of over the preferences of our agents, of our decision makers. The uncertainty might come from sort of lack of knowledge or restrictions in sort of the communication for expressing preferences or a variety of different contexts. And so I will write papers with my graduate students that have, borrow ideas for approximation algorithms and reproofs or some complexity results, but also kind of, how do we make trade-offs? Can we characterize the trade-offs in outcomes in strategic settings when we do have limited information? But I'm not just a theoretician. I also care very much about what it means to deploy some of these ideas in practice. So in that context, I work closely with colleagues at the University of Waterloo who do work in human-computer interaction to sort of help design the sort of platforms that can be used to support sort of human group decision-making. So on my middle slide is actually sort of an interface, which I didn't design, I was doing kind of the background stuff, that's being used in a medical context. We were designing kind of deliberation platforms for use for medical technicians that were sort of doing sort of complex data analysis using kind of medical time series data. Actually, in this particular context, it was in sleep studies. And so I was interested both in the usability, but also how can we support what sort of underlying algorithms are going to sort of best support, again, so this group decision making where the group was analyzing complex data. I also, some other application areas I work in tend to have a little bit of an environmental feel to them. So I work with some environmental lawyers where we're trying to understand what it means for laws to be effective and how are they supporting sort of sustainable development goals. And then I also work closely with people who work in the forest fire or wildland fire space, looking at resource allocation algorithms and the use of AI in that particular context. I'm happy to go into great detail about that because some really interesting kind of modeling and kind of risk analysis that you have to take into consideration there. But what I'm going to talk about today, as I said, is kind of a research agenda that some colleagues and I are pushing. And it has to do with cooperation. So cooperation, if we just think about it sort of in its broadest form, these problems of cooperation are ubiquitous. So a problem of cooperation, I'm going to define as a situation where agents, again, they could be software agents, they could be people, have opportunities to improve their joint welfare. So it's useful for them to actually work together, but there's going to be challenges. For a variety of reasons, it might not be easy for them to do so. It might be because of conflicting preferences or constraints, variety of different reasons. And these problems are ubiquitous. So we encounter them sort of daily. I mean, just scheduling a meeting among more than, well, if you have 2 people or more, just the scheduling of a meeting is a problem of cooperation where we both agree that we all agree that we'd like to meet, but actually finding a time slot can be quite challenging. It could be sort of working on kind of collaborative projects, or it could be sort of more complex. There's a lot of cooperation issues and challenges in an emergency response, where you have different agencies or units who all have to work together. And they all agree that they would like to achieve kind of sort of the same goal, but it's very difficult for a variety of reasons to do so. And then, of course, we can talk about sort of intergovernment negotiations. There are also often problems of cooperation. Now, when we think about cooperation and sort of human society, what's interesting is that humans as a species are really, really good at cooperating. And it's been argued that this is sort of really the main reason why humans have been so successful. We can cooperate both within our kin groups, and we also are very good at cooperating outside our kin groups. This makes us different from many, many other animals. Now, what we're seeing is, so over the last few years, sort of the advances in AI are such that they're being deployed. So we are using AI more and more in our daily life. And it's because they're being incorporated into our society, the last thing that we want is for these AI systems, or these AI tools, to disrupt kind of the cooperative structure that we have already kind of achieved in our society. So we're arguing that it's going to be important to equip kind of these AI systems that we develop with the capabilities that are necessary to both to cooperate and also to foster cooperation. Again, the last thing we want is to sort of destabilize a cooperation that we already have. Now, this is not easy, right? So it's going to require that the AI tools, systems, whatever we want to call them, that we design, are going to require both social understanding as well as what we're going to call cooperative intelligence. And so in a recent paper that appeared in Nature, sort of at the end of, middle of last year, some colleagues and I wrote a paper sort of as a call to arms, both to the AI community broadly, as well as to sort of, anyone who's interested in cooperation, where we were making the argument that cooperative AI, that now is the time to consider cooperation seriously inside the field of AI. And our argument, I'm going to take my notes because it was beautifully wordsmithed, not by me, was that if we're going to make progress towards socially valuable AI, well, our progress towards socially valuable AI is going to be stunted unless we put problems of cooperation at the center of our research. Now, in some subfields of artificial intelligence, in particular multi-agent systems, we have always been interested in cooperation. But there are other parts of artificial intelligence where that's not been the case, because it's just not that they're not interested in cooperation, it's just not being part of the model. And so we can look at the history of AI, and we have, for the most part, this methodological individualism. Now, any of you have ever taught an introduction to artificial intelligence course, probably one of your first slides you're going to show to your students will have something like those diagrams, those sort of box diagrams sitting there on, I don't know, what is that, your left, right? Where we have sort of an individual agent interacting with some environment, where that environment is inherently, it's non-social. Okay? We just ignore the fact that there's other agents. We ignore that they have this idea of cooperative intelligence is there. Now, this is absolutely the right starting point. Okay? Don't want to, this research and sort of these models have been very, very important, right? An artificial intelligence agent needs to understand the environment and sort of a single agent environment and how to interact with it first. Okay. But however, as we add agents and sort of begin to consider sort of the agent interaction, things become much more complex. We introduce sort of non-stationarity into our problems. We have sort of conflicting interests. The modeling becomes much harder. It's unclear kind of what the optimization or what the objective function should be. Now, you might say, hold on, there's sort of, AI has been very successful at some multi-agent problems. And that is true. In particular, there's been massive successes when it comes to AI in games. But cooperation is not just having multiple agents, something different. So we think about the games. We can go back to backgammon, of Jerry Tezzaro's TD Gammon program, or Jonathan Schaefer's Chinook for checkers, or more recently, sort of some really exciting progress in poker. These are multi-agent problems, but these are also not games of cooperation. They're games of conflict. Okay? There's a winner and there's a loser. So explicitly, there is no cooperation happening. Now, again, so this stuff is really cool. Like, I love the poker work. I think it's just amazing. But it's also easier. I'm going to argue that these sorts of problems are much easier than sort of problems of cooperation, because they're very easy to evaluate. For example, if you're playing Go, you have a winner and a loser. So you understand if you've designed a system which is playing really well. Okay? You win more than you lose. We also, in theory, the games the rules are really clear. The interactions are really clear, right? They're well written out, they're well specified. A lot of these games from a game theoretic, from a strategic perspective, are actually very simple. Not poker, poker's complex, but checkers, chess, Go are, in game theory terms, so extensive games of full information or perfect information, and we can solve them in theory by using backward induction, which is an algorithm that's been known for decades. Of course, the problem is just sort of the size of the search tree. In a cooperative setting, we don't have nice characterizations of what the solution should look like. It's unclear what it means to be cooperating well, or there is no notion of winning or losing anymore. And so the problems become sort of much more complicated and kind of messy. So when I talk about cooperative AI, what I mean is actually a broad umbrella term. So I'm going to argue that this is going to be AI research, which is trying to help sort of machines and also humans. Humans are going to be really important here, find ways to improve their joint welfare. Now, there's lots of different ways of cooperating. Okay, so it means that lots of different questions could be addressed under a cooperative AI agenda. So we can sort of think of just having like human-human cooperation. So I would say this is not cooperative AI because it's just two humans. As much as I love humans, they aren't AI systems necessarily. But we could move into sort of like cooperative tools. So a cooperative tool would be some sort of technology which could help humans sort of cooperate. This might be something like a machine translation systems, right? That could improve the communication. It could be mediators. It could be sort of programs or systems that help with negotiation, which is very difficult to do for humans as well as machines. Some of the work in AI alignment and safety are cooperative in nature, right? So where you're talking a little bit more about cooperation between an individual person and an AI system. So I would argue that could also fall within the scope. I think where things get more interesting around that bottom row, where we have sort of teams of humans and AIs trying to cooperate, who are hopefully well aligned, who are trying to sort of cooperate with other teams. We can also have a planner, like use an AI system as part of a social planner, which is trying to learn what are the good rules for how to structure the interactions which are actually being, or the actions which are actually being taken by people. And then finally, of course, we could have some sort of hybrid mismatch of all sorts of interactions happening between people and machines, or people and AI systems, and all sorts of different settings. And the approach that you're going to take in these sort of different scenarios is of course going to differ, and it's going to require lots of different sort of ideas and sort of methodologies. From both artificial intelligence as well as from other fields in order to make any progress here. So what we did in our paper, actually a couple of papers, we had the short nature one and then sort of a significantly longer one where we kind of expanded out all the ideas and provided examples, was to think about sort of what would be the pillars of sort of research that were going to be important to make progress on if we are to have, realize a stream of having kind of cooperative AI, so AI systems with social understanding. And we argue that there's four, right? So there's understanding, communication, commitment, and institutions. So when we talk about understanding, that's going to be kind of the ability to take into account the consequences of actions that agents, people or AI systems might be taking to predict others' behaviors and the implications of another's sort of beliefs and preferences. For communication, communication is also going to be critical for supporting cooperation. So you have to be able to, explicitly and credibly share information with others, which is going to be relevant to both the understanding of others and the others' understanding of you. We're going to need some form of commitment. So a commitment is the ability to make promises which are believable. I'll provide some examples sort of in the next slide. And then finally, we're going to require institutions. So institutions will be kind of like a social infrastructure. They form the guidelines, the norms, or the rules that agents and people need to follow and then support kind of this understanding, communication, and commitment. And hopefully if you have sort of good institutional structures, again, they could be informal or formal, then that will kind of lead kind of like, your entire system of people and AI agents to sort of good outcomes. Now, this is all quite abstract, so I was going to ground it a little bit in a particular application. And we'll use autonomous vehicles because it's so easy to understand. It also lets me show off the University of Waterloo's autonomous bus, which some of my colleagues work with. And again, I am not an engineer. I don't build autonomous vehicles, so I will talk about some of the modeling that we've been doing. So we think about autonomous vehicles, and I said that actually driving, whether it's an autonomous vehicle or just driving, people driving, is inherently a problem of cooperation, right? If you think about it, you're not driving in isolation. There are always other people on the road. There's other pedestrians, there's people riding bikes. So you have to understand them. And if we have autonomous vehicles in the mix, so the autonomous vehicles are also going to have to understand sort of the other drivers. They're going to have to understand sort of their preferences, their motivations, kind of their driving behavior before, if an autonomous vehicle is going to behave responsibly on our highways. They also are going to need to be able to communicate. And actually last night at dinner, we were sort of talking about examples about this, about a pedestrian crossing a road, and how what we often do is that as a pedestrian, you make eye contact with the driver. So if we are going to deploy autonomous vehicles on our roads, what is the right communication mechanism? Because it won't be making eye contact. It'll have to be something else. But that's going to be required if there is going to be any form of safe interaction between pedestrians and these vehicles. Autonomous vehicles will also have to have the ability to make commitments. So think about changing lanes. Okay, if you're changing lanes, you indicate that you want to move over into another lane, and the other car is indicating that they will slow down and let you in. I guess depending on what country you're in and so what norms they follow. And there's sort of an agreement there, right? It's implicit, but there's a commitment that if I pull over, if you allow me to pull over in front of you in the lane, I'm not going to stop and block you. I'm going to keep on going. So again, this is a commitment to follow through on an action that I have indicated. And so again, if we are to get to a stage where we have autonomous vehicles or on the roads with other drivers, we're going to need some sort of mechanism that will allow these commitments to occur. And then finally, and I think this is actually really exciting, we can ask the question, do we want autonomous vehicles on our highways with other, or in our urban centers with other cars? I think that's a legitimate question to ask. But if we have a population of drivers, particularly this really heterogeneous population, maybe the rules that we currently have or the institutions that we have aren't appropriate. Maybe there would need to be sort of different rules or traffic rules, different institutions in place that will help support kind of this cooperative behavior between different drivers or different vehicles. So this is sort of the high level problem or types of problems that I'm interested in. What I'm going to do for the rest of my time is to kind of get a little bit more specific to highlight some of the research which has been going on in my own group. Sort of that supports sort of these different pillars. And I'm going to be drawing a number of different examples, but there is sort of a common theme here. I'm going to give you one example about understanding, work that I say falls very clearly under the understanding pillar, and then very quickly, maybe if I have time, sort of two examples that would fall under sort of the institutional pillar. Communication and commitment I think are fascinating, but there's something which I don't have the expertise in to sort of talk sensibly about. So again, so what is understanding? Understanding is critical for cooperation. So when we talk about understanding, it's sort of taking into account the consequences of actions to predict the behaviors of others and sort of all those implications about another's beliefs and preferences. So there's lots of ways that we could think about sort of this understanding and different techniques that might be used. We can have richer game theoretic models. We can look sort of, additional work in preference solicitation and modeling, but there's also representation learning, inverse reinforcement learning, advances in the computational theory of mind, and so on and so forth. So I think it's a really, really rich area. I'm going to talk fairly quickly about sort of work that we've been doing on sort of preference modeling and sort of game theoretic models. So this is, again, in the context of autonomous vehicles. And it's a joint work with a sort of very, very brilliant PhD student, Patricia Sarkar, and then a colleague of mine in electrical computing engineering, Christos Stranaki. And what we are interested in knowing is how should an autonomous vehicle safely being critical here, handle other road users who might show complex and varied behaviors. Okay, so really like basic question when it comes to deploying autonomous vehicles. And there has been a shift in approach. So for quite a long time, there was this sort of predict and plan modeling. So you sort of learn sort of others' behaviors, and then you would kind of, sort of predict how they're going to behave and then plan from there. More recently, there has been interest in modeling sort of the so using kind of game theoretic ideas in order to capture the strategic interaction. So this that might occur. So there's this recognition that driving is a strategic problem. Now, the problem, however, is that human driving behavior is really diverse. A lot of game theoretic models make the assumption that you have fully rational agents, so they're expected utility maximizers, and that we understand so what the underlying preferences or utility functions actually are. And in the real world deployment, particularly when we talk about driving behavior, we do not have expected utility models. Instead, we're working with human behavior who are notoriously boundedly rational and have different risk attitudes. And so what we would like to do is to model both the diversity of human driving behavior, as well as sort of be able to compute kind of like appropriate responses from the safe responses from the perspective of the autonomous vehicle. And so what I'm going to go a little bit into the weeds here. So what we have proposed is a generalized dynamic cognitive hierarchy model, which sounds quite complex, but there's a lot of words there. But what it is that it's taking sort of a game theoretic model and adapting ideas from the behavioral economics literature and the psychology literature as to appropriate models of bounded rationality. And in particular, what this allows us, this multi-leveled procedure allows us to reason about kind of good responses or good strategies or trajectories that an autonomous vehicle should follow on a variety of different contexts under different driving behaviors and sort of risk attitudes and strategic reasoning capabilities of the human drivers on the road. And so we're leveraging sort of ideas from this thing called the cognitive hierarchy model, which again, sort of the quantum cognitive hierarchy model that again comes from behavioral economics literature. And so what we have is that we actually have sort of 3 layers. We recognize at our first layer that there are going to be drivers who are non-strategic. We allow for that possibility. These would be your drivers who don't pay any attention to any other cars on the road. And I think we've all encountered people who are like that. And it's also going to be useful for kind of like bootstrapping kind of some of our other analysis. And so for this particular application, what we've proposed is that we can use for these non-strategic, we call level 0 agents who only kind of just take actions, they don't reason about anybody else. We're using kind of automata strategies. But what you want is just something which is rich enough, non-strategic, but rich enough to have interesting behavior. The second level is the strategic level. This is actually used to capture the other drivers. So not the autonomous vehicle, but all the other cars on the road. And we allow for there to be different populations. So these drivers can be modeled by different models. So for example, in our particular instantiation, we include like a dynamic quantum model, which they're really cool. What they do is that they are strategic, but they assume that every other driver on the road is actually like this automata. And so you're best responding to this very simple population of agents. But then we also allow slightly more sophisticated models. So we're assuming that our agents are fully strategic. They're playing things which are close to sort of Nash equilibria, subgame perfect Nash equilibria. Those of you who like game theory, But we also allow for the possibility of sort of different preferences as well as mistakes, because it might have cognitive limitations. So we use something called a safety satisfying perfect equilibrium and a maneuver satisficing perfect equilibrium, which are sort of, you can think of them as or approximate equilibrium, but where sometimes the agents really care about safety and other times they really care about just getting to where they're going. Then at the top level is where we actually do our planning. So this is at the top, at our robust layer. We're actually, calculating the policy for the autonomous vehicle, but allowing, so that it's a safe policy, but allowing it to reason about sort of the behavior of the rest of the population by considering, by having beliefs over kind of this, what the different, how the different agents might be behaving, whether they are sort of these maneuver, whether they're playing a particular equilibrium strategy or whether it's sort of best response, whether just all autonomous strategies. And so this, we use sort of a robust or game theoretic approach, which means that we can provide solutions which are sort of game theoretically, strategically sound, but also have some particular safety guarantees in them. Now I'm going really quickly, but I just want to give you sort of an idea as to how we can leverage sort of ideas from game theory in order to organize kind of a reasoning structure that can take into account a very sort of heterogeneous population, sort of borrowing ideas from sort of the behavioral economics literature. Now, it's all very nice to be able to propose models. Of course, we want to be able to validate. And I won't show you the tables, but we were able to, this is a very parameterized model, but we were able to sort of find, learn sort of the appropriate parameterizations so that we were able to sort of match driving behavior in Canada. And we had a very rich data set also from Germany. Canadians drive differently than Germans, kind of interesting. And so we were able to just kind of say that yes, sort of like this particular, some of our design choices actually is flexible enough so that we can sort of fit models to kind of real data. And then we were also able to then, again in simulation, show that we were able to, using such an approach, kind of compute kind of driving policies for an autonomous vehicle who's reasoning about a diverse population, which are safe in a variety of complicated navigation issues, making complicated turns for intersections and stopping traffic in order to do parking and things like that. And so, as a proof of concept, this seems to work and provide kind of rich, safe strategies against complicated populations. So that was very fast, and I will, happy to take questions about that work later if you want. But I also then wanted to look a little bit at institutions. Now, when we talk about institutions, these are kind of rules which structure the interactions. And so, right, they can be informal, such as kind of social norms. So we often will hold the door open for someone. Okay, so slamming them in this place. That's a social norm which has arisen. Or an institution, we could say that's an institution. An institution can also be very formalized. So like the rules that describe how we vote in an election. That's another example of an institution. So institutions are sort of rules that we follow which will lead to kind of good outcomes for the population. So I have actually two examples here of what I'll call institutional work. One is only for agents, and the other one is actually we're working with people, so working with colleagues in HCI. So on one side, again, with a PhD student of mine, Dave Radka, who's actually a very, very good hockey player, so cares very much about teams. He was interested in exploring the role of teams as a way of promoting kind of broad cooperation across the population, if we have a population of learning agents. And so what we do when we have a team is that we're basically kind of changing the reward the agents receive. They're acting by themselves, they just get the reward that they get through their interactions. But if they're part of a team, then they kind of collect the rewards they share in the rewards that all their team members share. And if they're part of, and if we have a fully cooperative setting, that's as though we have like a team that involves everybody. Now, what we have done is that we've tested these ideas and trying to see whether team structures will actually improve learning. So these are learning, multi-agent learning agents, as well as sort of what does that mean for the, your mean population reward overall. And we've validated, run experiments across a variety of domains. These are results for one particular one called cleanup, which is an example of what's called a social dilemma. The idea is that you want to pick apples. You get reward for picking apples, but at the same time, you have to, in order for apples to generate or grow, they have to have clean water. And so you have to clean up the waste in the water, but you don't get a reward for doing that. And so there is kind of a tension here. It's a really kind of interesting problem because you do have this tension between only picking apples and getting reward versus going off and doing the hard work of actually cleaning up the water. Now, what he was able to show, and what I found fascinating, and interestingly enough, it also held in other contexts, including the iterative prisoner's dilemma, was the following, sort of this graph on the bottom. It's a little bit hard to read, but what we have here are different team structures. So that bottom orange line is where we have individual agents, and not on a team, they're only out for themselves. And we are measuring the mean population reward kind of over time. So it's an incredible number of steps. These are reinforcement learning agents, but it takes a long time to train. So we weren't surprised to see, your mean population reward is not very high if everyone's working as an individual. But what was interesting we found is that that bluish purple line is actually a fully cooperative setting. All agents are on the same team. Okay. And you actually do better, you can improve performance if you have smaller teams. Right? And in particular, these smaller teams do a couple of things. They allow for specialization. Agents are able to learn how to specialize much more effectively than if they are in this larger group. So in particular, we're finding that our teams would divide up. So some would collect apples and some would clean the waste. And so they could, maximize apple collection because they had their team members were cleaning for them. It also, we think, allows our agents to do a little bit more exploration. By being part of a member of a team, you're somehow protected. This is our hypothesis. You're somehow protected by some of the variance when it comes to sort of collecting these rewards. And so agents are more inclined or more capable of doing kind of interesting and sort of rich exploration kind of up front, which allows them to find find these good policies actually relatively quickly, compared to if they're either working as individuals or if they're all trying to, working all together as one large cohesive whole. Now, again, that's our hypothesis. But what's interesting is that we have found very similar behavior across a variety of other domains. It was not just in this cleanup domain. Again, I'm happy to talk in more detail about that also. On the other side, again, this is sort of give you an idea of some of the work we've been doing with my human-computer interaction colleagues. We're very interested in supporting group work. So you have a bunch of people working on some tasks that can only be accomplished by a bunch of them working together. And then there's some reward, which is given to the group, okay? Monetary reward, but it could just also be credit. And then we want to know, well, if you have a group project and the group is assigned a reward, how do you divide that among the individuals so that the individuals are happy, so that they consider that the reward division is fair? So we were designing platforms to support group work. And so we ran a bunch of experiments where we had our workers in Mechanical Turk kind of do some group projects together. And then we gave them different reward schemes. And we asked them, are you happy with this or are you not? And what was interesting is that, at least on Mechanical Turk, people liked getting paid more rather than less, but they also cared very, very much about fairness. They would, if we gave sort of unfair payments, they would point them out, and they'd point out unfairness, not just when it came and affected themselves, but also when it affected other people in their group. And even though these workers didn't know each other, everything was fully anonymized, they would still look at this group and say, no, this is no good. You're kind of cheating, worker number 2 over there. I don't like it. Now, what was less clear, however, of course, is what does fairness mean? And so in our initial experiments, what we had done, that one of our fair payment schemes was based on something called the Shapley value, which is an idea from cooperative game theory, and is considered to be called the axiomatic definition of fairness. So what we did is that we then went out and we asked people, what do you actually think? If I give you a kind of a group situation where there's a group reward to share, how would you divide it up? And so we ran experiments and we compared those suggestions, these reward divisions, with actually what the Shapley value predicted. And what's interesting was that even though there was a lot of structure in the way that people would report what they considered to be fair, it didn't actually align up with the Shapley value, which meant that some of the axioms of fairness from the cooperative game theory literature are not valid when you're working with certain populations of people. So, so why is this interesting? Well, it means that if we are going to design sort of payment schemes for group work on these different platforms, we can't just blindly take ideas from the literature. Instead, we need to understand kind of what trade-offs that we're making. Now, what's nice about these axiomatic approaches is that they are very clean. They're easy to explain because we know what properties they have. So we don't want to lose that. So what we've been proposing is that we look back at our data and use data-driven approaches to validate axiomatic approaches. And what we found in this particular set of experiments is that even though Shapley's axioms were violated, there was still a lot of structure, and there was particular weakenings of the axioms, which have been studied in the literature, which actually did describe our data sort of very nicely. High statistical significance, we could say that certain acts or weakenings of the axioms were supported. So this then opens up the space of, for example, ways of designing rewards if we are going to design platforms for group settings. Now I think I'm almost over time, so I'm going to sum up very quickly. What I've been arguing for is kind of this direction of research, very broadly, that we're calling cooperative AI, which is our AI research trying to help humans and machines find ways to improve their joint welfare. And I think what's quite exciting is that that has to be sort of highly diverse. So it's going to rely on sort of expertise from a variety of different areas. It could be sort of AI and multi-agent systems and game theory and HCI, that's sort of the space that I like to work in. But also we're going to need insights from political science and economics and sociology and psychology, because they also think very hard and very seriously about cooperation and will have insights that are going to be important as we go forward and design these AI applications. So in summary, hopefully trying to get into that, cooperation should be at the center of AI research. And what makes it interesting, that's unlikely, if you ignore cooperation, it's unlikely to just kind of emerge by itself. So it's unlikely to be kind of emerge as the byproduct of other forms of AI research. It will have to be inherently interdisciplinary because it will rely on kind of ideas across a wide range of different areas. But it's also going to be difficult to do because as we move from individual objectives to shared, poorly defined ways that humans solve problems, how do we measure progress? Like, what are the right benchmarks? What are the right properties that we're actually looking for? And it's unclear. So I think there's actually going to be significant work is going to be required just to think about what questions we should be asking and how we should be evaluating progress. Okay, thank you.